All right. Okay. So, students of 805 and 812, welcome to our first lesson today. Okay. It's like 7:30 in the morning. So if I lack enthusiasm, I think you can understand. Okay. I like just got here basically. So yeah. So this is our first lesson today. So every day when you see this, whether you're even if you're in school or when you're at home doing math, I'm just gonna, show my face and tell you what we're going to do in class. Okay, very brief. I'll try to keep the videos 20 minutes at most for the time being. I really don't want to take up too much of your time, knowing that you still have a lot of obligations that you have to take care of. So, with that said, today we're going to do the first lesson, which is number families, which also include a throwback, okay, to all the way back to February. So, yeah, okay, so let's get started. Hello, everyone. So, yeah, here's our lesson. All right, Unit One, Day One. All right. So the essential question. So this is important. All right. Sometimes when I post essential questions, I don't even read it. So, but today we're going to try to answer this question. Are all numbers real? Now I put the word "real" in quotation mark, and I'll explain to you in a second what that means. So first of all, do now. So let's get to do now real quick. Okay. You could probably do this as I'm speaking. Now again, I'm not too inclined to give you guys do now questions actually when you walk in, because again I'm trying to help you focus on the lesson for the day rather than anything that's extraneous. So okay, since this is our first lesson, right? Typically there wouldn't be a do now if you're doing this at home, all right? And then on the right side is the date, and then also announcements. Now, I used to make announcements in class, but sometimes that ends up taking 10 to 15 minutes. And again, like we don't have that luxury right now. Okay, so just read this. Okay, the announcements are here. If you guys have any questions ever, uh, when we see each other in person in school, or you can email me. I can answer questions that way. Okay, I think that's the best way to use time. So real quick, all right, I'm just gonna do this. Okay, now I'm hoping that in the seventh grade you learn the rules for adding and subtracting, multiplying, dividing positive and negative numbers, right? So when you add with two signs, what do you do? Two same signs, not two signs. When you add with the same signs, what do you do? When you add with different signs, what do you do? Right? When you add with different signs, what do you do? And then when you add with the same signs, what do you do? Right? Okay, this one is not a trick question. Okay, all right. Okay, so let's see. All right, let's get to the lesson. Okay, so what are we going to talk about? We're going to talk about families of numbers today. So the number family, we're going to talk about some definitions. So in order to do this, I actually made this video for a group of students earlier in the year. So I'm not going to make the video again. So what I'm going to do is I'm going to edit the original version of the video. So we're going to do a little throwback. All right, this was done 8 months ago, I think. So, and the lesson, I'm not trying to brag, but I think I did a pretty good job explaining this. So without further ado, I'm going to put in, all right, I'm gonna put in the video for from what is it, 8 months ago, and then when we're done, we're gonna come back. Okay, all right, let me press pause. Okay, so let's jump into it. Okay, all right, so this is the family of numbers. So if you want, you can copy it down in the way that this is presented. All right. If not, you can just list them out. So let's start with natural numbers. Now, some of these might get, how do I say? It might get very lecture-like, might get a little bit philosophical, but that's okay, all right? Because my goal here is to try to mimic as close to an actual lesson as possible. And I really hope that, you don't just know the definitions, but also know the meaning behind these definitions, and really understand where do these numbers and the categories come from. Okay, so the first one is, okay, if you were to think about numbers, right, as they were first invented, probably thousands of years ago.
right? When the human being, we're hunting and we're looking at, we see animals, right? If you see one animal, right, you can conceptualize that there is one. So in some ways, even animals can count. For example, the animals can count in groups of 3s and 4s. Okay, so they don't say 1, 2, 3, 4. So they can look at a group of animals and split them by easily manageable groups. So like 3 and 4, so they kind of know that there's 7, right? So likewise, if we see one, I don't know, zebra in the wild, and then we see another one, zebra in the wild, naturally, we can make the conclusion that there are now 2 zebras in the wild, right? So that's the birth of arithmetic, all right? Arithmetic just means operation with numbers, okay? So that's a study, that's a branch of study of mathematics. So here, when we're talking about natural numbers, we're talking about numbers like 1, 2, so on and so forth. Those are natural numbers, meaning numbers you can count, actually. So for example, you can't count 0, right? And you can't actually count negative numbers. So that's a natural number. Now, what's a whole number? So a whole number, it's a series of numbers where you don't have any decimals or percent or fractions. So 0 is a whole number, right? So is 1, so is 2, so on and so forth. That's why, as you also see, these circles become larger and larger because they're just a family. So in other words, in a set of all whole numbers, natural numbers is one of them with the exception of 0. So 0 is a whole number, but 0 is not a natural number because you can't find 0 in nature. Like it doesn't, like there's no number that stands out like that. Okay? So moving on into a larger and larger family, now we have integers. So what are integers? Well, integers are whole numbers, but now they include 0. So all the whole numbers. All right? But they also include positive and negative numbers. So now you got -1 and -2. Okay, so that's what integers are. Next, rational numbers. Rational numbers, you can remember rational numbers by looking at this word ratio. What's a ratio? Yep, it's a fraction. So any number that you can put in as a fraction, like 2/3, or as a decimal, like -2.7, all right? Or another fraction like 1 1/4, right? These are rational numbers because they can be put in as a fraction. So for example, if I were to ask you, hey, can you write 0.5 as a fraction, what would you say? Right, you say 1/2, right? 5/10, which is 1/2, right? As you can recall from the decimals unit. So that's how you do that, okay? Now, so what are irrational numbers then? Having said that, irrational numbers are numbers that you cannot put in as a ratio. So no ratio. Now, that's strange, right? Because you all your life you're in math class, and you learn that you could put things as ratios, as fractions, as decimals, percent. So you would assume that everything can be put into a ratio. So for example, right, even 100, it's a rational number. Why? Because you can put in 100 as a fraction, right? It'll just be 100 over 1. Whereas irrational numbers are numbers like this, pi, right? Because pi is actually a non-terminating decimal. So the question is like, how are you going to write a fraction where the answer, so to speak, if you were to convert from a fraction to a decimal, where the number is a non-terminating, non-repeating decimal? All right, now another rational number is square root of 2. All right, now you will explore that further in high school, so I won't get too deep into that, okay? And then now you're talking about real numbers. So what are real numbers? Okay, well, this is the whole family of real numbers. So that begs the question, right? Is there such a thing as an unreal number? All right, maybe I should type this, but all right, too late. Is there such a thing as an unreal number? Yes, there is, actually, all right? And we call those imaginary numbers, all right? So this is deep into high school territory. So if you're not quite understanding what I'm saying here, it's okay, all right? This is a little bit beyond your age group here. So what's an imaginary number? It's a number. So for example, all right, now I'm going even deeper. So for example, if I were to ask you, right, what's the square root of 4? Which means something like this. What number multiplied by itself will give you 4? So what times what? Using the same number will give you 4. What would you say? Yep, 2. Right? So for example, let me ask you another question. What's the square root of 25? In other words, what number times itself will give you 25? What would you say to that? Yep, that's right, it's 5. So that's what a square root is. So where am I going with this? Well, imagine, right? You have a square root of 1. What's the square root of 1? In other words, what number times itself will give you 1? Yeah, 1, right? 1 times 1 gives you 1. But the problem is then, what number times itself will give you negative 1? And the answer is, well, there isn't any. Right? Because 1 times 1 is 1, and negative 1 times negative 1 is also 1. So again, now we're going into 7th grade territory. So what they do is they would use the letter I to denote that this is an imaginary number. It doesn't exist for the sake of math. Okay? So, all right, I just had a couple of visitors. Where was I? So yeah, imaginary numbers don't exist, but like I mentioned in class on several occasions already, sometimes mathematicians perform mathematical operations, maneuvers, let's just call it that way, all right, for math's sake. It's like solving a puzzle for the puzzle's sake. Now, I'm sure there's some genius out there that, can rebuke what I said, because I'm sure there's probably some practical application to the imaginary numbers, but perhaps I don't have the intellectual capacity or the time to actually go over that. So all right.
Okay, all right. So I hope that all of you find that helpful, all right? And it's also important, like you just have to know at some point what all these definitions are, okay? And the discussion regarding imaginary numbers I thought was very interesting, okay? Sometimes people do math just for the sake of doing math, okay? It's like a game. And I actually would also like all of you to take that approach when it comes to, especially in the 8th grade with a lot of algebra. Like, treat math like a puzzle, all right? It's just a puzzle that you have to solve. Like, don't get intimidated by the type of numbers you see, okay? It's just a puzzle you have to solve, and in the beginning you might not figure the puzzle out, but by the end all of you are going to be able to figure the puzzle out, okay? And that's when it gets fun, okay? So be patient with yourself, okay? All right, so in the video I already talked about what irrational numbers are. So irrational numbers, right, cannot be written as a simple fraction. So for example, right, here we got a 1.5, right? That's a ratio. Now, in other words, think about this. Even in 6th grade, right? Remember if your teacher gave you something like this, right? And you have to write this. You can write it as a fraction, which assume that you have to write this as a fraction sometimes, which is already making the assumption that you are capable of writing this as a fraction. Now, with my 6th graders, all right, back in the day, I would say something like this. You write it like you say it. So how do you say this? Right, 67 what? So this is tens, that's hundreds, right? 67 hundredths, right? 67 hundredths, right? So that's how you would, so you write it like you say it, okay? However, with pi, which you might have done this last year, even though, you know, we had locked down early. Not sure if you got to circles, but the letter pi, right? It's a Greek letter, right? The Greek letter pi, right? It's a non-repeating, non-terminating decimal. So non-repeating means it doesn't repeat. Non-terminating means it doesn't end. It keeps going. So I'll give you two examples of that, right? Repeating would be something like this, right? That's repeating. A terminating decimal would just be something like this, right? Now this can keep going, obviously, right? Okay, so that's that, all right? So that's what I mean, repeating and terminating decimals. Okay, so pi it's not rational because you cannot possibly write a non-terminating, non-repeating decimal as a fraction. Okay, all right, so it's not rational, irrational, like, you know, the word irrational, right? Makes no sense, right? That's the definition. Okay, so, all right, so rational, so these are some examples of rational numbers, right? Even 7 is a rational number, right? Because you could put 7 over 1 here. 0.333, right? Repeating is 1/3, right? Or the other way that you could write it is this, right? Okay, all right. Now, again, pi, right? Look, I'm sure that, you know, again, in the 7th grade, back in the day, all right, some math teachers have these pi digit memorization contests, okay, where people have to memorize the most amount of digits, all right, of pi, all right, to win the contest. So as you can see, like, it just keeps going. Like, if you have enough space, you can just keep going forever and ever. Okay, so that's why it's probably the most famous irrational number. Okay, by the way, feel free to pause if you feel like you want to take notes. Sometimes I will tell you exactly when to take notes. Okay, so also I'm also open to the idea of someone giving me suggestions as to how to keep a virtual notebook, because I looked into it yesterday. I want to keep a virtual notebook so you guys don't have to spend all the time like copying stuff. But I'm looking at Google presentations and I'm trying to find the ultimate solution to this. So if you guys have any suggestions, let me know. All right. Let's see. Okay. All right. Okay. Moving on. All right. Now, here's some other famous irrational numbers, and that is the square root of 2. Now, in the video from 8 months ago, I already spoke about square roots, right? So you should know at least what the idea of a square root is. So the square root of 2, so square root of 4 is 2, so that's a rational number. So the square root of 4 is also a rational number. Here's the problem. The square root of 2 is not a rational number. Now, how will you know, right? Because some of you say, well, yeah, but Mr. Ring, how am I supposed to know this, right? Square root of 2 is irrational. So I would say this, right? If you put the square root of 2 in a calculator, okay, which if you don't have a scientific calculator at home, you can take your iPhone, right, and you can go to the calculator function, and you could turn it horizontally, and I think somewhere around here, there's a symbol like this. So what you do is you press this, right? And then you put the number in that you want, and then you will get something that it's gonna look something like, it might look something like this with the 2 inside. It might look something like this, and then you press equal or enter, and then it'll give you this very, very, very long number till the calculator runs out of space. So in other words, the square root of 2 is an irrational number. Now, having said that, put in the square root of 3, square root of 5, and square root of 7. What do you realize? Yeah, right? You see what I'm talking about? Okay. And then what about, Even if you put in something like 26, right? What do you see? Right? So as you can see, if you put in the square root of 4, square root of 9, square root of 16, like these are called perfect squares, by the way. Perfect squares. U-A-R-E-S. Okay, perfect squares. You're going to get a whole number and rational. Okay, when you put in 3, 5, 7. All right, you can see where that's going. Okay, let's see now. These are some very famous irrational numbers. All right, pi. This is Euler's number, which you will use when you are in high school when you deal with logarithmic functions. All right, logs. Okay. Golden ratio, I didn't even know that's how you write golden ratio. And then square roots, right? Many square roots, okay? What are the exceptions? Think about that. What are the exceptions? Which square roots will give you rational numbers? Right, perfect squares, right? Okay, all right, okay. Now, let's see. Now, I have an optional video for you guys. So because here, now what I've said begs the question, right? Why are only non-repeating, non-terminating decimals irrational? So in other words, what about terminating decimals? Why are terminating decimals rational, right? I explained this earlier, okay? So I'm not going to explain it again. Or repeating decimals. So this is important. So why is 0.111111, so on and so forth, right? Why is that rational? What would the fraction look like, right? Because the definition of rational is to put it in a ratio of fraction, right? So why is it a fraction then? Okay, what would the fraction look like? So that's why I have this logo here. So I've attached a video, all right? I can't embed it into my own video because I don't think I can have a video where I show someone else's work from YouTube. So I'm gonna attach a link with the video. You can watch it. It's really good. Now, if you don't have the time, you don't have to watch it. It's optional. But for now, just take the word, okay, that repeating decimals are rational. Okay? All right. Now, let's move on. Now, how are we doing on time? I might have to stop it here. 12. What was it? 12 plus another. Yeah, I got to stop it here. Okay. You know what? Let's do this, and then I'll feel pretty good about where we're at, and then we'll start with day 2 tomorrow. Okay, so let's see. Perfect squares, right? 4, 9, 100, right? 25. All right, what would these be? What's the perfect? By the way, it would also help if you know like this. Okay, I'm just saying. Okay, all right, so, yeah, even 225, right? Is it 225? All right, I might make a mistake here because I'm in a little bit of a hurry. So, right, square root of 4 is 2, square root of 9 is what? What times what gives you 9? 3. By the way, if I ever go too fast, do a couple of things. Pause the video just to make sure, you know, you absorb the information I'm giving you. And second, tell me. Like, just say, Mr. You're going too fast. Like, you gotta have to slow down, okay? I don't mind doing that, okay? So that's 10. That's 5. What's the square root of 121? So what number times itself gives you 121? That's right, 11, right? What about 144? 12. 196? Do you guys know what it is? Think about it, okay? Press pause right now if you need to figure it out, okay? I'm gonna let you press pause right now. Okay, all right, have you guys thought about it? What would that be? Yeah, 14, right? And what about 225? Yeah, 15. Okay, important question. I'll put this in green. What about the square root of 1? What times what gives you 1? Yeah, 1, right? What about the square root of 0? What times itself gives you 0? 0. Okay, all right, not bad, not bad. All right, so yeah, let's stop here, all right? Do the homework, and I will talk to you guys tomorrow, okay? Thanks for watching, and have a great day.
OMG, that was so good.